Equilibrium position in a system of electric charges. We will take it now from the concept of electric fields. The equilibrium position in a system of electric charges indicates the position where the electric fields are balanced, which means that they have equal magnitudes and they go in opposite directions. In other words, it means that the resultant or the net electric field at that point should be equal to 0. We will use the same rules as the ones we used for the electric force. For a system of like charges, the equilibrium position is located between the charges next to the one with a smaller or less magnitude. And for a system of unlike charges, the equilibrium position is located outside the spacing between the two charges next to the charge with less magnitude. So again, it's always next to the charge with less magnitude. This is an example. Find the equilibrium position in the system shown below. How to do this task? First of all, we check the polarities. The two charges are positive, so they are like charges. Then the equilibrium position should be somewhere in this space between them, next to the smaller charge. We compare. QA is 2 nanocoulombs and QB is 5 nanocoulombs, so QA is smaller. Then the equilibrium position is close to QA. We put it there. This distance is 10 meters. If I assume that this distance is x, then from N to B, it should be the total, which is 10, minus this part, which is x. So 10 minus x. Now, the next step is to draw the electric field vectors. QA is positive. So its electric field diverges away or points away from A at all points. So at point N, it diverges away from A in this direction. So it's pointing or diverging away from A. QB is positive. So its electric field also diverges away from B in all directions. So at point N, it should be pointing this way to point away from B. So this is EBN. Since we have state of equilibrium, then we will say that EAN is equal to EBN. EAN is KCQA over RAC squared equals EBN, which is KCQB over RBC squared. KC and KC, they cross out. Then we have QA over RAN squared equals QB over RBN squared. Now we replace. QA is 2. RAN from A to N, we have a distance of x meters, so over x squared. QB is 5 nanocoulombs over 10 minus x squared. No need to convert because they are both in nanocoulombs. So if this was 2 times 10 to the power of negative 9 and this one was 5 times 10 to the power of negative 9, the conversion will cross out. Now, next step is not to cross multiply, it is to square root both sides of the equation. So square root of 2 over x squared equals square root of 5 over 10 minus x squared. We simplify, it will be radical 2 over radical x squared is x. Radical 5 over radical of 10 minus x squared is 10 minus x. At this point, we cross multiply. We will have radical 2 into 10 minus x equals radical 5x. So 10 radical 2 minus x radical 2, we distribute radical 2 over the brackets, equals x radical 5. We do the calculations. We move this part minus x radical 2 to the other side, it becomes positive. We take x as a common factor, then x is equal to 10 radical 2 over radical 5 plus radical 2, which is 3.87 meters. As you see, N is located at a distance x to the right of QA. So I have to write to the right of QA. Another example, locate a point P in the system shown below where the net electric field is 0. We have two negative charges, so they are like charges, then the equilibrium position is between them next to the smaller charge. So point P is close to the minus 2 nanocoulombs. When we have negative charges, remember that the minus sign indicates the polarity. When I want to compare, I compare the magnitude. This one has a magnitude of 2 nanocoulombs. This one has a magnitude of 4 nanocoulombs, so this one is smaller. We follow the same procedure. We assume that this distance is x, then this distance is 10 minus x. We draw the electric field vectors. So the electric field created by A at B, A is negative, then its electric field converges in, so it should be pointing towards A in this direction. This is EAP, and B is negative, so its electric field also converges towards B. At point P, it should be converging towards B. EAP equals EBP, the same thing. KCQA over RAP squared equals KCQB over RBP squared. KC and KC, they cross out. We will get QA over RAP squared equals QB over RBP squared. We replace QA is negative 2 nanocoulombs and it is at a distance of x from point P. QB is minus 4 nanocoulombs and at a distance of 10 minus x from point P. Now square root both sides. So radical 2 over x equals radical 4 over 10 minus x. Cross multiply, square root of 2 into 10 minus x. Radical 4 gives out 2 times x, so 2x. Rearrange the formula to keep the factors with x on one side, so move minus x radical 2 to the other side, it becomes positive x radical 2. Take x as a common factor and find the answer for x in meters. And again, point P is at a distance of x to the right of QA. Another example, locate the equilibrium position in this system. So, this system is a system of unlike charges. We have QA is 2 nanocoulombs, QB is negative 5 nanocoulombs. Always remember the minus sign for the charge indicates the polarity. So, the rule for unlike charges is that the equilibrium position is outside the space. It's not in this space, not within this space, it's outside. So it's either on this side or on this side. So we have to check which charge is smaller. This one is 2 nanocoulombs, this one is 5 nanocoulombs. Again, forget about the polarity, we're just comparing the magnitudes. So QA is smaller, then I will add the point on the side of QA. QA is a positive charge, the polarity is positive, then its electric field diverges out or points away from A. So at point N, it should be pointing this way away from QA. QB is negative, so its electric field converges in, so it should be pointing towards the QB from all points. So from point N, it should be pointing towards B, this way. Now we apply the concept of equilibrium. Then this is x, this distance is x, then this distance from B to N is 10 plus x, the whole thing. EAN equals EBN, so KCQA over RAN squared equals KCQB over RBN squared. We cross out KC, then we have QA over RAN squared equals QB over RBN squared. We replace the values, A is 2 and B is negative 5. The distance from A to N is x meters, from B to N is 10 plus x meters. Square root both sides, then we cross multiply. We distribute the square root of 2 over the brackets, and then we rearrange the formula to keep x on one side. Take x as a common factor, x into square root of 5 minus square root of 2 is equal to 10 radical 2. Then x equals 10 square root of 2 over square root of 5 minus square root of 2. And we get the answer as 17.2 meters to the left of QA. So N should be at 17.2 meters to the left of QA. Another example, QA is negative 4, QB is positive 2, unlike charges. Then the equilibrium position is either on this side or on this side. It's not between them because they are unlike charges. We compare. QB has a magnitude of charge of 2 nanocoulombs. QA has a magnitude of charge of 4 nanocoulombs. So QB is smaller. Then the point should be on this side. I put point M there. I will draw EAM. Since QA is negative, then the electric field of A converges towards A, so at point M it should be converging or pointing towards A in this way. And since B is positive, then its electric field diverges away at all points, in all directions. So at point M it should be pointing away this way. Now if this distance is x, then the whole distance from M to A will be 10 plus x. The same rule, EAM equals EBM for this system to be at equilibrium.